Hi, Brian Maestri, Mississippi Valley Division economist, using the Coastal Texas CSRM study to discuss storage tank depth damage relationship development. To develop these depth damage relationships, so first we'll discuss the methodology that was used, the available information on the storage tanks, and then the results and conclusion. First, this is in the Galveston, Houston area, and the Houston Ship Channel is basically running through this area. And you can see there's approximately 4,600 storage tanks with GPS locations in the Houston Ship Channel area shows. The little inset at the top is a sort of like a satellite view from way far away, and you can see it's a little bit to the east of the city of Houston. And then in the middle is a blow up of the area with all of the tanks. And in that you can see the location of those tanks, and you can see a square, a little pink square, and it's blown up at the bottom showing you the that particular area in the storage tanks located there. So this is a unique benefit category to try to look at how flood risk can be reduced for these and to try to quantify that and include it in our NED damages and benefits. So going to the next slide, as you can see, with just what I discussed, it's a non-traditional NED benefit category. We try to develop generic depth damage relationships for the physical damage to the tanks, and also the value of the material that would spill out of those tanks when there's failure. And one of the reasons why we were able to include this category, because to my knowledge, this was never included in any other core study, was we had some unique information that Drs. Camishaw and Dr. Pageant shared with us from a journal article on storage tanks and their fragility assessment of those in a 2016 article. And that information allowed us to incorporate this benefit category. So the methodology was taken from that journal article, and it's basically, does it float? Flotation failures created when uplift created by the storm surge is greater than the weight of the tank. A buoyant tank floats away from its foundation, and it begins to spill its contents. The Archimedes principle, which is a Greek mathematician, engineer, he calculated buoyancy forces and the whole methodology back in the days when the king, he wanted to know if the crown was full with gold or silver, and he was able to put it into a bathtub and see the weight of it and how it affected, and he could tell by the height of the water whether it was buoyant or not, that, oh, it was filled with something of a less material, silver and not gold. And he used these principles anyway to develop all the mathematics behind that buoyancy, and those principles are still being used today. And so here it's being applied to the forces that buoyancy forces exerted on a storage tank due to storm surge. So the model parameters, what makes a tank buoyant? The buoyancy force, the density of the seawater. The more dense it is, the more likely to float. The higher the inundation level in feet, the more likely it is to float. The acceleration of the water due to gravity and the height of the storage tank. And the things that resist buoyancy, and all of this was put into their equations, was the thickness of the tank shell, the base, the roof shell, the relative density of the steel, the amount of liquid stored in the tank, and the relative density of the storage tank itself. So all of those parameters were put in, and then of course behind every model there's the assumptions. The amount of liquid is uniformly distributed, meaning between 0 and 90%, meaning that there's as much chance of it being 25% filled as there is being 60% or 70% or 50%. It's between 0 and 90%. It's a uniform probability distribution. The contents are unknown. However, the contents had upper and lower bounds based on the Texas Commission of Environmental Quality permits. And as soon as that tank starts to float, all of the contents spill out. The effects of attached pipelines are not included, and The tanks are commonly unanchored, and that's what is assumed for this analysis, because that's what was observed. The regression model then predicts the flotation of storage tank for given parameters and inundation depth. So based on that depth of water, that's one of the main things that determines whether or not the tank floats. Monte Carlo simulations were performed to reproduce the uncertainties in the liquid level and the liquid densities, and to obtain the failure probabilities and the expected spill volumes. So the failure analysis only considers flotation failure and not failures due to buckling or debris or wave impact. So that's how you typically see your storage tanks driving around, and especially if you're looking from above the circular cylinders. And this was the specific information that we had on all 4,600 tanks. And what I did is I just took the minimum tank size in terms of size, then the one right in the middle, and then the largest tank. So you can see, just looking at these cost of tanks, the minimum tank was only $25,000. Most of the tanks were around like $281,000. And you can see the largest tank was a big one, almost $6 million. And we had the longitude, the latitude. That's how we got to show you those opening slides and the location, the diameter, and the height and the density, and all of those things. We had that information. And so from their journal article and in the models, then they developed the failure probability at various levels of inundation at each 1 foot. And so you can see here's the probability that the tank would fail, that it would float. And then the proportion of the capacity spilled at the various levels of inundation is shown here. And again, it's once it fails, it spills everything, but what's the probability of that happening? So that's why you have pretty, relatively low volume amounts of being spilled, because the chances of that happening aren't very good, and that's worked into the expected values. So we had that information, and we wanted to apply that to the storage tanks. Now, we couldn't have 4,600 depth damage curves in our model, so we wanted to develop one generic depth damage relationship to apply to these storage tanks and to all of the other storage tanks in the study area, because this was just a Houston ship channel area. So that's what we took on, is to develop those depth damage relationships in a generic way to apply to all of the tanks and incorporate the uncertainty based on that information we had. And as you can see, the rest of the study area, there's actually, we talked about 4,600, there were actually almost 13,000 tanks in our area, in region 1 of our study area, the Galveston-Houston area. So we incorporated generic depth damage relationships into our analysis. We developed a structure inventory, and it had unique ground elevations and values assigned to each tank, just like as if it was a residential or non-residential home. We applied the without project and with project stage probability relationships, just like we would to our structure inventory. And we had uncertainty incorporated around the depth damage relationships, the ground elevation, the value of the tanks, and the stage probability relationships. And here you can see the structure records. There's a structure name, a unique ID. We have it's a storage tank. We got the station, the location for it to apply the stage probability relationships, the water surface profiles. We have the structure value in thousands of dollars, 187,000. That's the value we came up with. Now later on, we had to incorporate, that value was reduced because we had to incorporate depreciation. That's the replacement cost, but we had to incorporate depreciation. And then here you can see the ground elevation or the stage, and that was there, and then the module name. So what were our results in developing using all the information that we had on the 4,600 tanks? Well, the average value was $187,000 once you incorporated depreciation. And then we had our minimum value and our maximum value. Now, we didn't use the absolute maximum and the minimum because we were doing a triangular probability distribution. So you use the 1% and the 99%, not the absolute maximum and absolute minimum, because if you remember, the 1%, the minimum value was actually around $25,000, but when you take into account a low end range, you develop bins, a range of values that make up the lowest percent. That's how, and you can see that there was only one tank like it was near $6 million. So, but when we develop a range, you put them into statistics, into bins, and we had it in 20 increments. That was our range that we had. And so the average, the most likely value was $187,000. In terms of the value of the contents, the way we estimated that is we took what was being shipped into the Houston ship channel. And we had the proportions of those, and we had the 3-year average, not just using any 1 year, because you know oil prices, how they can change. So over a 3-year average, and we got those, and we developed a weighted average to apply to the contents. And once we did that, taking into account the amount of material at the banks that the tank could hold, actually the material in the tank was worth 4.15 times the value of those tanks. So what was in it was a lot more valuable, which isn't surprising than the actual physical value of those tanks. And you can see we had the range. And so again, it's not just one number, we got a range here. And so from all of that information, we developed structure, depth damage relationships, the most likely value. And you see we got the 1%, we got a range in the 99%. So that became like a triangular distribution with a most likely value, a minimum, and a maximum value. And again, your minimum is not the smallest value, but it's once you put it into that group of which you classify as the minimum values. And there's your range. And you can see at different depths of flooding. So just like we would apply to a residential or non-residential structure. And then we did the same thing for the contents. And again, once the tank failed, it spilled all of its contents, but this is on an expected value basis because the likelihood of that is small. So the spill volume may not be as great as you would think, but that's for one tank. But then when you start multiplying by all the tanks, it gets up to be a large value. So we ran the dam. We had those were our inputs, our economic inputs, used along with the stage probability relationships, our engineering inputs. And we calculated the damages without project were $110 million expected annual damages, or approximately 3% of the total without project damages. The benefits was 63 million, over 63 million, almost $64 million expected annual damage, or a little over 3% of the total benefits for the recommended plan. To get approval for this, if you're using a non-standard benefit category, you first got to check with your local, with the vertical chain, and get approval and for using this. And they said yes, this is an NED benefit category. It fits that, and it's a non-standard. But we had enough information to do what was a good enough job in terms of reducing the uncertainty surrounding that. So we got approval from all the way up at headquarters. So make sure whenever you have a non-standard benefit category that you do let the vertical chain know, and then you got to get approval for that. There's actually the regulations require. So my concluding remarks on this is, when you do these additional benefit categories that are not traditional ones, non-standard, you got to determine if the benefits could affect decision making. One of the things we had to consider is, do we want to include storage tanks? Because it takes study funds in order to do this. And we made that decision that there's 13,000 storage tanks in this study area, and it's something that we should include for this particular study area. If there were only a few of them, or less than 50, we would not have taken this on. The other thing is to use your study funds wisely when estimating non-traditional NED benefit categories. So which categories do I want to take on? And again, it was based on the magnitude, and then, does it make a difference? And whenever you incorporate these non-standard categories, incorporate risk and uncertainty in all your benefit calculations. So I think this shows you that the HEC-FDA model, the structure inventory, is not just necessarily for residential and non-residential structures. It can even be applied to storage tanks. So there's a lot of flexibility with the model, and it really is an art and creativity to use the model in a way that that you can incorporate these benefit categories into your analysis. So I just wanted you to see that and have an appreciation for that. Normally, if this was a regular class, I'd be taking questions, but since we're in a virtual world, I'll just say, I hope, I love economics. I hope I can give you an appreciation for what we do in economics, and I hope this was helpful. Brian Maestri here, nice to have you there, and let me know if I can help you, and I'll be seeing you.